So welcome to the Fluids and MHD seminar. So today we've got Reun. So he's now at the University of Cambridge at DEMTP as a Newton International Fellow. And before then he did a PhD in Marseille with Favier and Lebars on the work that he'll be talking about today, and the work he's done since then on that work, on the nonlinear saturation of the elliptical instability, on wave turbulence versus geostrophic turbulence.
All right, so thanks Adrian for the introduction, and thanks for inviting me today. Okay, so I'm going to try to, here is the pointer. So yeah, I'm going to present the core of my PhD work that I did with Benjamin and Michael, and we also benefited from a very useful input from Adrian that you know very well, and Basil, who is working at CEA in Saclay near Paris. So the motivation for my work is trying to understand and describe the flows in planetary cores. So planetary cores are those envelopes that you find in rocky planets in the depth of deep inside the rocky planets. And it's an ocean made of liquid ions, which is a electrically conducting fluid. And so it can be steered by motion, which can be created in two ways. The first one that you may think of is thermal convection, because those planets used to be hot and they are cooling. So you have cooling by the top of the cores, and very much like in this pot of hot chocolate, you can have convective motion inside the planetary cores. The other forcing that can steer the interior of planets is a gravitational interaction through the effects of tides. So tides are very well known at the surface of the Earth for driving very intense, large amplitude and large scale flows in the oceans. And it can actually also drive motion inside liquid cores. So why is it interesting to study fluid motion in planetary cores? So one of the reasons is that those motions, because they happen in an electrically conducting layer, they can drive dynamo action and create a magnetic field that protects the Earth or other planets from harmful cosmic radiation. And they also change the rate of tidal dissipation inside the bodies. So they ultimately control the orbital evolution of planetary systems such as the solar system. And today I'm going to focus on tidal steering of motion inside planetary cores, which is particularly relevant to small moons of the solar system, such as Ganymede or Io, which are known to have a magnetic field that can be explained by gravitational forcing. Okay. So what are the ingredients that you need for tides to excite motion inside a planetary core? So the first one is, of course, tidal distortion. So when you have a companion body, it exerts a tidal force that distorts the planet and creates a bulge that is symmetric around the axis joining the two bodies. And the other ingredient that I'm going to focus on today is one that is particularly relevant to the small moons that I just mentioned. For instance, in the case of the Earth moon, you have spin orbit synchronization, which means that the period of spinning of the moon is equal to the period of orbiting of the moon. So if you take this moon, so say the Earth moon or Ganymede or Io, when it rotates, when it completes a quarter of its orbits around the planet, so the Earth or Jupiter. So it also rotates on itself by 90 degrees. And if the bulge is initially in this position, then when you are at a quarter of the orbit, then you have a misalignment between the tidal bulge and the planet, which results in a net gravitational torque. that tends to accelerate the spinning rate of the moon. And the opposite effect happens at the 3/4 of the orbit, where the misalignment works to decrease the rotation rate of the moon. So at the end of the day, you have variations of the rotation rate of the moon, which is called libration, and this is what I'm going to study today. So let's consider the most simple form for libration, which is a rotation rate that is modulated harmonically at a certain frequency. The first response of a planetary core to this kind of forcing is this kind of flow, which is an oscillating solid body rotation, well, almost a solid body rotation, because you have small departures because of the ellipsoidal shape, and those small departures are proportional to the ellipticity of the tidal deformation. So what you're seeing here is the flow that you get and that you see when you're sitting at the north pole of the planetary body, and you're peering into the core. So this is the flow that you would see. That's not the end of the story. This flow can't drive dynamo action, for instance, because it's too simple. But this oscillating flow that is also homogeneous in space can drive other fluid structures in cores. So for instance, in rotating fluids, you have waves called inertial waves that are spontaneous oscillation that result from the action of the Coriolis force. If you look at the Euler equation, the linearized Euler equation with the Coriolis force here, and you look for plane waves, you can find that this equation sustains plane waves that have this dispersion relation that relates the frequency to the angle between the wave vector and the rotation axis. And frequencies are bounded between -2 times the rotation rate and +2 times the rotation rate. And what happens is that when you have libration at a certain frequency f, this tidal flow here excites a resonance, an exponential resonance of a pair of waves at half the frequency, which is called, so this kind of instability is called a parametric subharmonic instability. And in this particular case, it's also called the elliptical instability because of the elliptical shape of the flow. So this is quite well known, and has been studied by many people before I started my PhD. And what was not very well characterized was the turbulence saturation, as the exponential growth of those waves stops and they collapse into other structures through nonlinear interaction. And yet it is this region that is interesting to explain or describe dynamo action or dissipation. So this is really what I'm trying to address here, which is the turbulence saturation of those tidal instabilities. So here's the outline for the rest of my talk. I'm going to address this problem in 3 different ways. I first talk about an experimental study that I will complete with idealized numerical simulations, and at the end I will propose a theory that accounts for the findings that I've made. Okay, so here's the experimental setup. So we have our planetary core here, which is an ellipsoid filled with water, and it's mounted on. So it has an ellipsoidal shape to mimic the tidal distortion. It's mounted on a turntable that drives the constant rotation rate, and on a secondary motor that drives harmonic oscillations of the rotation rate. And we track the flow through PIV.
These flows in the lab. We use an
okay, so I'm going to show now. So it's advertisement movie that we made in the lab about the experiment. So there is a voice that you possibly can hear. I hope you can. So this guy has a better English accent than I do, so I will just let him speak.
These flows in the lab. We use an egg-shaped or ellipsoidal container filled with water to model a core distorted by tides. It is set on a rotating table with a secondary motor that allows to reproduce the varying rotations of moons. The results are striking. Our experiments are able to produce motions at different scales which favor the emergence of a magnetic field. However, we cannot experimentally study the dynamo process since water, which we use in our setup, does not have enough of these flows in the lab.
Okay, so you get the
these flows in the lab.
Sorry, you get the picture of the experiment, which is quite massive, and of course water is not electrically conducting, so we can't do any dynamo action. Okay, so with these experiments, what are the regimes that we hope to explore, and how do they compare to geophysics? So we have three dimensionless parameters. We have the forcing amplitude, or the Rossby, which we call the Rossby number, which is proportional to the ellipticity of the deformation, and to the amplitude of the modulation of the rotation rate, the amplitude of the libration. There is also the libration frequency. So in the case of the moons that I discussed earlier on, it was f equals 1. For us, it's not very practical because the growth rate isn't that high at f equals 1, and we want to have large growth rate to have more turbulent motion. So we use f equals 4, which allows us to optimize the growth rate of parametric subharmonic instabilities. And there is also the Ekman number, which quantifies the effects of viscosity compared to the Coriolis force. Okay, and if I plot a regime diagram, so dissipation or Ekman number versus forcing amplitude or Rossby number, of course, geophysics is at very small dissipation because of the massive size of the bodies, and at very small forcing amplitude because the tidal deformation are quite small. And previous work are, of course, very far away, so in very dissipative and high forcing regimes. And what we hope to do with this experiment is this small leap that looks like quite a small leap towards geophysics. But as I hope I will convince you, it will still be very useful to understand better the physics of tidally driven turbulence. Okay. So I'm going to show a few experimental movies that I hope won't buffer too much. So the first one is I started the solid body rotation. The interior of the ellipsoid has reached solid body rotation, and I just turned on the libration flow. So you just see the PIV particles going back and forth. So you just see the base flow, the libration base flow. Okay, so there's nothing very interesting yet happening. And if you wait for a few minutes, then you see, if you focus in the center, if you look carefully, you see that you not only have the back and forth motion of the libration flow, you also have radial motion that's happening at twice the period of the libration period. So what you're seeing here is an inertial wave that's growing at half the frequency compared to the libration forcing. In fact, at this frequency, the inertial modes that you excite have a pancake-like structure, and with the PIV setup, we are just getting through one of them. Okay, so that's the growth of the instability. And once you reach the saturation, you see this kind of very complicated flows where hopefully you can see that you have many different structures, and it's quite messy. So we would like to understand really what's going on in this flow. So to do that, the most the most straightforward way is to use temporal spectrum of the energy of the kinetic energy of the flow. Why temporal spectra? Because you have very clearly identifiable structures in the flows. You can separate structures by their frequencies in the flows. For instance, you have the libration peak here at F equals at the frequency of 4. At half the frequency 2, you have the resonant wave, and you can filter out the fields to extract it. In this range here, you have inertial waves, so their frequencies bounded up to 2, and you can also extract them. And you have at 0 frequency, you have mean flows, and they have the property to be, so they are called geostrophic modes, and they have the property to be invariant along the rotation axis, which is perpendicular to the plane of the slide. Okay, so and so for this, the first experiment that I showed that was at a small Rossby number, so about 510 to the minus 2. What we see is many peaks in the inertial wave range, so many inertial modes. And what's striking about them is that you can pair them by 2. You can make pairs, and when you sum the frequencies in one pair, you get the frequency of the resonant wave. So the frequency of this one plus this one is equal to the frequency of this one. Same for this one and this one, this one and this one, etc. You get the picture. So you have many waves that satisfy this particular relationship. So what's really going on here? Okay, so I should mention also that you can also extract the spatial structure of the modes. So you can see that they have a large scale organization. And if you look at the azimuthal wave numbers, the resonant mode has an azimuthal wave number of 1. And when you look for a pair, the difference between the azimuthal wave number of this one and this one, so it's 2 here, 1 here. So the difference between those is 1, and 1 is the azimuthal wave number of the resonant mode. So those pairs, what are they telling us about the flow? So what are we seeing? So to understand a bit more of that, we can look at the Euler equation that we recast into this form, where you have a linear operator with eigenvectors that are the inertial modes, and eigenvalues that are the frequencies of those modes, and a nonlinear operator that's coupling those modes with one another. If you decompose the flow as a superposition of inertial modes with their eigenfrequencies, then you can find the amplitude equations so how energy is transferred from 2 modes to another. And you can see here that energy transfer is optimal when you have this relation that is satisfied for the frequencies. So when the sum of the eigenfrequencies of the daughter waves of the daughter modes is equal to the frequency of the imposed mode. And hidden in this term, you also have the similar condition on the wave number that I explained just on the previous slide. So what we see here is triadic resonance, what we call triadic resonances, which are instabilities of waves that are not directly excited by the libration flow, but that are excited by the resonant mode. So what we see here is a wave-dominated regime, wave-dominated saturation. Okay, so what happens if we crank up a bit the Rossby number? So we go from 5 times to the minus 2 to 6.8 to the 10 to the minus 2. If you look to the flow, I hope that you can see that in the center, it looks very different. This time you have a persistent swirling flow at the center of the ellipsoid that is anticyclonic. And so it's a mean flow, right? It's persistent, so it's also invariant along the rotation axis that is perpendicular to the plane of the slide. Okay, so can we quantify a bit more how this mean flow emerges? So of course, just by averaging the fields, we can extract it and measure its RMS amplitude. So I'm just mentioning here that those flows are called geostrophic flows because they correspond to a balance between the Coriolis force and the pressure gradient, because they are quasi steady. And if you compute the RMS amplitude of those mean flows as a function of the Rossby number, you see that there is a quite sharp transition from a very weak mean flow to strong mean flow by just increasing the Rossby number. So that was at one particular value of the Ekman number, but you can also track it at different Ekman numbers. And what you see here is a secondary transition that's happening in the saturation of the primary instability, because it happens well above the threshold of the elliptical instability. So we have a secondary transition. And it's really a geostrophic dominated regime, because if you look at the temporal spectra of the flow, you see that although you had peaks in the wave dominated regimes in the inertial range, they tend to be completely blurred for the geostrophic dominated regime. Okay, so we have two very different regimes of saturation here. And just to summarize the experiments, you can put them all on a regime diagram. So forcing amplitude versus Ekman number or dissipation. So the black dots are the wave dominated regime, and the red diamonds are the geostrophic dominated regime. And I've also put some previous work where they didn't clearly identify, well, it was quite, well, there was also a transition from weak mean flow to large mean flow. And you see that the boundary between those two regimes is quite consistent. So yeah, so we have this secondary transition that seems consistent between previous works and experiment, but that is a bit better characterized. And what is really new here is this wave dominated regime that was evidenced, I think, for the first time in this experiment. And with that, we made one of the last few hardcovers of JFN. We were very happy about it. Okay, so with this setup, we have found a new regime, which is a wave-dominated regime, but it is still quite dominated by viscous effects, and we would like to explore this regime in a more asymptotic limit where dissipation becomes very small and and forcing amplitude is also very small. So we can't really do that with experiments because it would be an unreasonably large experiment. With global simulations of a complete ellipsoidal container, that would be unrealistic. It would be more difficult than in an experiment, actually. So what we do is we resort to local simulations. We assume that the turbulent flow in the planetary core is homogeneous. So when it's driven by tides, it's homogeneous. And we just simulate one small patch that we take a simple geometry. So we take a cubic geometry and we take periodic boundary conditions. And this simple geometry allows us to use very efficient pseudospectral methods. And the tidal flow is just in the background and accounted for by shearing box modeling that was developed in the Snoopy code, developed by Geoffroy Lesure, and later adapted to the case of tidal flows by Adrian. Okay, and again, we make a small leap from the experiments towards geophysics with simulations, but I will show that this small leap will also allow us to understand a lot regarding those flows. Okay, so to start with, let's just do a simulation, but in a regime that is quite close to the experiments. So I put here the location of the simulation in the regime diagram. So the Ekman number is about 5 10 to the minus 6, so quite close to the experiment. The Rossby number is about 7 10 to the minus 2, 2, yeah. So also quite close to the experiments. And we have just changed the frequency, but it doesn't change very much the physics. Okay, so initially you see the waves, the inertial waves that are growing, except that this time they take the form of plane waves. And is there a question or something, or? I think it's fine. Okay, and after, once you reach the saturation, then you see here a geostrophic dominated regime that's clearly identifiable by those eddies that are invariant along the rotation axis. And they undergo an inverse cascade, and you end up having two counter-rotating vortices that take all the space in the box. One question that you can ask here is, do you still have waves in those geostrophic geostrophic flows? So to answer this question, we project the energy of the waves into the space of the dispersion relation. So we represent the energy as a function of omega, the frequency, and theta, the angle between the wave vector and the rotation axis. So we do that by taking the flow in the real space, the velocity in the real space. We do a first Fourier transform to get the flow as a function of the wave vector case, and we integrate this flow on the case that have the same angle theta, and that allows us to have a representation of the flow as a function of theta and t. And we do a last Fourier transform, this time in time, along the time axis, to get a representation of the flow as a function of theta and omega. And you get this kind of diagrams for the energy, where I've put here the dispersion relation of inertial waves. And you see that initially the resonant modes and the resonant waves are on the dispersion relation at a frequency of 1.5, which is where you expect them to be because it's half the forcing frequency. At later times, once the elliptical instability has reached saturation, you see very well the geostrophic modes at the end of the spectrum here at 0 frequency and theta equals pi over 2. And you also see a blob that is sort of around the dispersion relation, but not in a very convincing way. And the energy is all over the place once you've reached this ultimate state of saturation. So in this case of geostrophic saturation that we observed also in the experiment, we do not really see inertial waves per se. And the trouble with this setup is that because geostrophic modes are quite unconstrained, right? You don't have any reconnection with the boundaries to dissipate them. They are very free to grow, and even if you decrease the forcing amplitude or the Ekman number, you always end up with this type of flow. But we would like to study still the wave-dominated regime. So what we do is that to mimic this reconnection with the boundary, we had a specific friction to the geostrophic modes to force them to be subdominant. And by doing so, we retrieve three-dimensional turbulent states. If you look at the energy as a function of the frequency and the angle, you see now that the energy is very well focused along the dispersion relation. So here we retrieve really the wave-dominated regime, as in the experiment. But now we would like to explore more asymptotic regimes. So I'm going to focus now on those 3 simulations where, in fact, more like this one that has a very small Ekman number, so 5, 10 to the minus 8, and a very small Rossby number, so I think it's 7.5, 10 to the minus 3. Of course, we have a completely three-dimensional flow which has a lot of small scales, and you see that you have a continuum of waves along the dispersion relation. And so energy has been injected right at this point, only through the resonant waves, and we have filled the entirety of the dispersion relation by nonlinear interaction. And also this filling of the dispersion relation is also associated to a cascade of energy from the resonant modes that have this wave number towards smaller scales with a typical slope, typical decay law with a k to the -3 slope. Okay, so what we see here is something that looks like wave turbulence. So what is wave turbulence? It's a state where where you have many waves that are in nonlinear resonant interaction with one another. So in nonlinear triadic interaction with one another, and you have this turbulent flow that results from the statistical equilibrium of all those interactions between all those waves. And this kind of, so wave turbulence is a general object in physics that has been observed. It's a general theory that has been observed to describe flexural waves on plates. It can also describe sea states during a calm day in summer, like here in Brittany back in 2019. And in certain regimes, it can also describe stratified turbulence. So how can we prove that here we do have inertial wave turbulence? The nice thing with wave turbulence is that contrary to the Kolmogorov, three-dimensional isotropic turbulence, you can really take a certain asymptotic limit of the Navier-Stokes equation and derive a spectrum for the kinetic energy of the flow as a function of the wave number. And this has been done in the case of inertial waves by Sébastien Galtier in 2003. And it is quite anisotropic because the spatial repartition of energy through scales depend on both the perpendicular and parallel component of the wave vector with different exponents. So are those exponents found in our simulations? So it seems like it is the case in our simulations. So here I've extracted the k perp and k parallel contributions to the spectrum, and you see that we see the -5½ slope that was predicted by Galtier, and we sort of see the -½ slope here, although it's not entirely convincing, and we think that to be entirely convincing, we would need to have injection of energy, so resonant wavelengths at a much smaller scale, which is not really doable at the moment with the numerics. But still, what we conclude from that is that the wave-dominated regime of tidally driven turbulence is described by wave turbulence theory. So really a swarm of waves that are in nonlinear resonant interaction with one another. Okay, and another thing that I would like to show before switching on something else is, so you may think that the friction that we have used to retrieve the three-dimensional state of turbulence is quite artificial. And in fact, what I'm going to suggest here is that it's not that artificial. It actually allows you to explore different states of rotating turbulence that you wouldn't have accessed otherwise. So this is the case here, where I'm looking at this particular simulation here, and so I do a first simulation where I start by creating a wave turbulence by putting the friction. And at some point, I remove the friction and let the geostrophic flow evolve freely. And you see that although it increases a bit initially, it reaches a plateau and remains completely subdominant for the rest until the end of times, compared to waves. And if we start without friction at all, then we switch back to the geostrophic saturation for the same values of the control parameters, right? So we have bistability of rotating turbulence at small Rossby number, which is quite new, and also it shows you that friction really allows you to explore different states of rotating turbulence. Okay, and I think it's important to note also that if you decrease the Ekman number, so if you decrease dissipation, you switch back to even if you start from a three-dimensional state, you switch back to the geostrophic state via a very nice exponential growth. Okay. So that's it for the numerical simulations. And the last thing I would like to discuss today in the remainder of the talk is a theory that possibly accounts for all the findings that we have made with both the experiment and the numerics. Okay, so we would like to explain or to describe and predict the transition between the wave-dominated regime and the geostrophic-dominated regime. And what are the clues that we have regarding this transition? Well, we have this curve, this experimental curve of the RMS of the mean flow as a function of the Rossby number. It looks like you're hitting here the threshold of some instability of the geostrophic flow that becomes unstable and grows and takes all the energy in the flow. The other thing that suggests an instability is the bistable simulations that I just showed. And in particular, this simulation, when you release the friction, you see the exponential growth of geostrophic mode. So you see that those clues really suggest that we have an instability of geostrophic flows. And but it remains to be found. So to explore that, I'm using again the code Snoopy, but instead of modeling tidal flows, I'm just looking at the stability of one inertial wave. So I'm just looking at the stability of this flow. So this imposed wave that has an eigenfrequency of 1.8 or so. And I fix this amplitude. I'm going to call this amplitude the Rossby number. And if you do that with a very small, well, quite small wave amplitude, you see that waves, well, 3D perturbation grow exponentially. So that's the kinetic energy as a function of time. They grow exponentially. Whereas geostrophic grow later and with a growth rate of that is twice the growth rate of the three-dimensional perturbation. And if you look in the energy as a function of frequency and angle, you see that you have those two patches of energy that are along the dispersion relation. And again, if you sum the energy of this patch and this patch, you get the energy of the resonant wave. So what we see here is, again, a triadic resonance of two daughter waves that is excited by the primary wave. And geostrophic modes are not unstable here. They're just directly forced by the growing waves, but they are not unstable themselves. And so here I'm just repeating what I just said. And it's different when you increase by an order of magnitude the wave amplitude. Then you see that the geostrophic modes grow together with the waves or the 3D modes, and they grow with more or less the same growth rate. And you can also spot them in the dispersion relation diagram at the end of the dispersion relation. Although you still see traces of the triadic resonance instability that we saw earlier. But here we also have geostrophic instability that's kicking in. And we can extract the geostrophic mode that is growing, and it is this mode. And what I'm going to do next, so those simulations were initiated with the noise. And what I'm going to do next is using these modes, well, this mode that has been extracted as an initial condition to test the growth rate. So I'm going to use as initial conditions those modes PG that are geostrophic. So they have no component along the z-axis, along the wave vector doesn't have any component along the z-axis. It's z invariant. And I'm going to consider 3 different values of the y wave number. So 1, 3, and 5, and knowing that 5 is more or less the mode that I have extracted in the previous simulation. And you see this quite peculiar shape for the growth rate as a function of the Rossby number, where at moderate to high Rossby number, it seems to be quite linear. But as you decrease the Rossby number or the wave amplitude, there is a finite amplitude beyond at which the growth rate goes to 0. And it seems that the smaller PGY is, so the smaller this number is, the further you can go, the smaller the critical Rossby number can be. Okay. But we still don't know what's really going on with this instability, and that's really told by the frequency, the spatiotemporal diagram of energy, where you see here the geostrophic mode, and what you see here is in fact the signature of triadic interaction, because you see this spot of energy here is exactly at the location that you expect for the mode Q here that closes the triad between K and P, the geostrophic mode that we've put as an initial condition. So we see here that we have triadic interaction, except that this time it's not a triadic resonant interaction, because this patch of energy is not centered on the dispersion relation. And in any case, if the triadic resonant instability condition were matched with a geostrophic mode, there is a theorem by Greenspan that tells you that you can't have a geostrophic instability. So we really need to have a non-resonant interaction to observe energy transfer. Okay, so we have a triadic near resonant instability, and we can describe it in theoretical terms. So with K imposed, we can derive the amplitude equations of the mode P, which is geostrophic, and the mode Q, which closes the triad. And the time evolution of the amplitudes of these modes is described by those 2 coupled equations, where the time variation of the amplitude of P, say, is described is proportional to this coupling coefficient, which is purely a function of the wave numbers, times the amplitude of the imposed waves, times the complex conjugate of the other wave in the triad, times this oscillating term that oscillates at the frequency, which is the sum of the three eigen frequencies, and which is non-zero. This term is non-zero here. And if you look for exponentially growing solutions, you can find this value for the growth rate, this expression for the growth rate. And you can also compute those coefficients for the particular modes that I've used in the simulations. And here I have superposed the theory with the numerics, and you see that the curve that are given by this growth rate law describes very well the theory. Okay. So we have a near resonant instability. And now we would like to go back to the general case, which is if you impose a wave and you put a noise, what is the mode that's gonna emerge? What is the most unstable mode? Or in other words, what is the upper envelope of all those growth rate curves? So the problem is, given a certain Rossby number, what is sigma? And the maximum of sigma, sorry. And the important point here is that the coupling coefficient with the geostrophic mode, P, is proportional to the detuning delta omega. Okay, so when delta omega goes to 0, so when you draw closer to exact resonance, this growth rate goes to 0. But if you take a certain, if you take a certain Rossby number and you plug that into that, you see that the delta omega is going to be proportional to the Rossby number squared. So that means that sigma is the square root of Rossby number squared times Rossby number squared minus something times Rossby number to the 4. So in the end, and you can go further in the math, in the algebra, you find that at small Rossby number, you expect the maximum growth rate to be proportional to the Rossby number squared times the wave number of the imposed wave. And if we look at the DNS that use noise as an initial condition, you can clearly see that the DNS follow the envelope of all the growth rate curves that have been computed on all possible geostrophic modes, and moreover, they stick to this theoretical prediction here. So we really have a good theoretical understanding of the instability, at least in the small Rossby number range. And we see that at larger Rossby number, it's no more k Rossby square, but it's more like k Rossby. And with that, I can make a small leap towards the conclusion. So what is the regime diagram of this instability? What is the viscous threshold? First, what is the viscous threshold of the instability? So to retrieve the viscous threshold, you balance the inviscid growth rate that I've just derived with friction. So say here a wall friction. Imagine a wall friction that has a square root of Ekman number dependence. So this Rossby square law here gives you, when you do the balance, Ekman 1/2 boundary between the unstable geostrophic mode and stable geostrophic mode when you plot the Rossby number as a function of the Ekman number, and Rossby proportional to Ekman 1/2 at larger Ekman and Rossby numbers. Okay, and with that, so that brings me to the conclusion. So with the experiments, we have found two different regimes of saturation. We have found a geostrophic type of saturation, and this one is very well known in the literature on rotating turbulence. There are many papers dealing with geostrophic vortices in rotating turbulence. And what is really new here is that we found purely three-dimensional states, and we have proved with idealized numerical simulations that these three-dimensional turbulent states are wave turbulence. And with the theoretical analysis, we kind of understand why we have this Ekman 1/2 line here that separates the wave turbulence from the geostrophic turbulence. And we expect that as you go towards the geophysical regimes, what looked like a sweet spot, in fact, becomes a wider and wider area where wave turbulence becomes predominant. And it happens that geophysics that is located at this end of the regime diagram, wave turbulence is actually relevant for those regimes. And this opens quite interesting questions. For instance, we don't really know yet what is the magnetic field that you can get out of wave turbulence. There is a paper by Keith Moffat in the 1970s that said that you can have alpha dynamo from a random superposition of inertial waves as long as you break mirror symmetry. But is it the case for wave turbulence? So that's still an open question and ongoing work at IRFE at the moment. And same for the dissipation. There is still much work to do to fully understand what's going on with the wave turbulence. And with that, I will stop here, and I will thank you for your attention. I'm happy to take any question. Thank you.